So welcome everyone. Today we're very happy to have Andrej Risteski from CMU speaking for us. He's an assistant professor there in the machine learning department, and he will tell us about two works that study the interpretation of attention weights in transformers. So Andrej, please go ahead.
Thanks, Tim. Thank you so much for the invitation, and thanks for organizing this seminar. It's a very nice sort of like thing, and it's a great resource for the community. So I'll talk about a couple of papers that are sort of loosely connected by this kind of idea of trying to understand what kinds of patterns can you hope to find, and when these patterns are kind of misleading, by looking at sort of some simple kind of sandboxes that isolate some aspects of linguistics, and maybe just to sort of get us a little bit like, in the right zone. I'll start kind of very high level to kind of do a little bit of a kind of overview and situate where kind of what the motivation for and the philosophy of this work is. So kind of maybe at the sort of super highest level, what is sort of like, the kind of the maximally hopeful promise of interpretability methods. So in some ways, kind of the story is that we hope that what these methods can deliver is that we can somehow kind of understand these black boxes that we get after training some, big complicated machine learning method. And the hope is that we can kind of understand what the algorithm that implement is. And if we can do that, then somehow we can do it well enough, then we can maybe debug it. Maybe we can certify how good its performance is, like, and maybe sort of steer it in some ways, and so on and so forth. And sort of some maybe like, short list of deliverances of this approach on the empirical side mostly, just to kind of mention a couple. So there have been some cases where people look at some relatively simple task, like maybe modular arithmetic, and then they can kind of, in some ways, recover or reverse engineer what kind of algorithm the trained model is implementing. So perhaps kind of the most famous example here is this very nice paper by Ananda et al., where they were sort of kind of reverse engineering some kind of Fourier-based algorithm for doing modular addition. Another sort of also kind of famous example is this kind of work by folks at Anthropic, where they were trying to kind of identify some useful submodules in trained models, in particular things like induction heads, by kind of like a variety of sort of probing methods. And then kind of perhaps even more recently, the sort of deliverances of these kind of reverse engineering methods can also be used to in some ways debug failure modes of some kind of relatively complex large models. So what I'm showing you here is a screenshot from the recent, I guess it's not a blog post, kind of an announcement, I guess, of the new nonprofit Transluce, where they were trying to kind of showcase their interface for how you could use sort of a battery of interpretability methods to try to debug some failure modes in trained models. So in this case, there was like a kind of very famous bug that a lot of large language models were experiencing, where if you kind of, where for some reason they seem to think that 9.11 is bigger than 9.8. And so what you can see on this kind of little interface is, it's trying to kind of identify which neurons are responsible for this. And if you kind of, I'm not sure how kind of visible this is, but you can sort of see that there's a neuron that it identifies that has like, some sort of something to do with 9/11. And then like, one conjecture is maybe it interprets 9.11 as a date, like 9/11, and then it thinks that 9/11 is bigger than 9/8 because it interprets it as dates. There's also some like, other sort of neuron which has sort of something to do with the Bible, and then like, they think that maybe one reason is that it interprets this as like, the book and verse, the chapter and verse, sort of 9:11. So again, that's sort of why it thinks that the sort is the wrong one. And then the hope is here that if you can kind of debug these things in this way, then you can kind of edit them in some way and steer them to do more like, the things that you want to do. So what I'm showing you here is again some screenshot from a very nice recent paper by Gandhi-Kora et al., where they're sort of again using a battery of these interpretability methods to try to take the pre-trained, in this case multimodal models, and sort of make them conform to some prerequisites that we want them to conform to. So maybe you want to remove nudity, so kind of moderating NSFW content, or maybe like, erasing some artistic styles which we think that shouldn't be there because of copyright reasons, and so on and so forth. So this is sort of like on the kind of optimistic positive side. Of course, this talk is going to be a little bit more on the kind of cautionary side. So there've been some kind of cautionary tales over the years as well. Perhaps sort of in the even kind of in the relatively early days of interpretability, there was this kind of very nice paper by Zach Lipton, which sort of pointed out a variety of ways in which the kind of concept of interpretability can be sort of somewhat philosophically loaded and slippery, and oftentimes can mean a lot of kind of heterogeneous things. And oftentimes we may want some kind of desiderata out of like implicitly out of interpretability that sort of are at the very least like not completely spelled out in papers, and oftentimes can even be at odds with each other. For methods that somehow try to reverse engineer a variety of types of algorithms. So for instance, this kind of paper that found this like Fourier algorithm for modular addition. There's also kind of recent works which suggested these results can be sort of very non-robust in the sense that small changes to the training method, oftentimes even things as little as initialization, can in fact result in sort of algorithms that seem very different. So there's this kind of nice paper by Zhang et al., which sort of finds these two algorithms for doing modular arithmetic, which they call the pizza and the clock algorithm. And this has something to do with like doing again something in Fourier space, and the sort of the pizza and the clock algorithm referred to sort of some pictorial way to represent these operations on a little circle. And then there's also sort of results that suggest that oftentimes the kind of a variety of these kind of interpretability methods are often sort of misleading even in more serious ways, in the sense that they don't even pass some kind of simple sanity checks. Perhaps maybe the token paper here, this nice paper by Adebayo et al., sort of again, early days of interpretability in 2018, where they basically show that there's sort of a variety of sanity checks, like checking how much the output of the interpretability method depends on the the data being like real data as opposed to random data, or like the weights of the model being the trained weights versus like random weights. And then oftentimes a variety of these methods somehow don't really strongly depend on like these aspects, and you would of course naturally expect them to depend on them, and you would want them to. So this is also kind of like an early paper containing a cautionary tale. So okay, what is this talk going to be about? So in some ways, at the end of the day, most of these kind of like empirically deployed methods for interpretability just don't come really with any guarantees. And of course, as theorists, we'd like to sort of like make them somewhat more reliable, and we'd like to develop some kind of theory to understand kind of when they're like giving you sort of the right signal and when they're sort of misleading you. And sort of the primary difficulty here is the usual one that we have in the era of modern deep learning, which is that the data that you're using to train the models and eventually sort of use the interpretability methods on is sort of very complex and heterogeneous. The models that we train are often very large, like they're very intricate. So this all kind of makes developing theory kind of challenging. And the kind of approach that I'm going to be advocating in this talk is that in some ways, if we want to understand these methods, or at the very least kind of debug them and be able to understand when they're giving you something reliable or not, is to kind of try to understand them in sort of simpler sandboxes. And by a sandbox, I mean sort of some setting which is simple enough that we can kind of theoretically analyze it, at least partially in some ways, but it's also kind of illustrative enough that it pinpoints some failure modes that we're trying to understand. So for instance, we can kind of ablate away aspects of the data to only contain some aspect that we're trying to understand. So in this case, in today's talk, I'm going to talk a little bit about topic structure as cashed out by topic models, and some simple ways to model syntax by context-free languages. And then also possibly maybe we want to also simplify the architecture that we're trying to understand them on. So rather than like, some complicated, like, deep transformer-based model, maybe we try to understand them in some like, simpler, shallow, maybe even one layer attention model, again, to kind of try to poke and understand possible failure modes. So at the highest level, I'm going to tell you two stories. One is going to be about kind of common bag of words model that's used to kind of model topic structure in documents called topic models. And I'm going to sort of tell you that in some sort of like simple model of a very ablated transformer, basically just like one layer of attention, there's a sort of very predictable and interpretable way in which the structure of the data, in this case the topics, gets encoded sort of in the learned weights or attention of the transformer when you train it with sort of standard gradient descent-based methods. That's going to be takeaway one. And takeaway two is going to be for kind of even for more complicated sort of structures than topic models, but like still very simple structures. So for very simple kind of context-free grammars, in particular, it's some kind of like language that kind of models very simple aspect of grammar by looking at sort of validly nested parentheses. It's already, the picture is already very different. So somehow the training can converge to many sort of qualitatively very different solutions. And there's actually not much predictable, interpretable that you can say about sort of the structure of the attention that you're going to converge to at the end of the day when you train these models. Okay, let me dive into the first part. So I should say that both of these works are sort of largely done in collaborations with students of mine. This kind of first work was spearheaded by Yuchen, who's in the audience, and then the second work is with a bunch of students, and it was spearheaded by Kaiue, who was an undergrad who was visiting at the time. So let me kind of give a shout out to them. Okay, so let me give you a little bit of preliminaries. So the sort of most basic preliminaries that I have to write, and I sort of fully appreciate that some of these things might be entirely obvious to a big chunk of the audience, but I presume it's there's a mixed in background, and also this is going to get eventually going to be on YouTube. So just to make sure that everybody's on the same page. Let me sort of write out the sort of bare bones mathematical form of what an attention layer does. An attention layer is kind of the basic building block of a transformer. So this is sort of the idea. So you have a sequence of length capital N, and for each of the sort of tokens or each of the elements in this sequence, I have some way to encode them. In this case, I'm going to imagine that there's some kind of vocabulary which is of size D, and the sort of the kind of encodings of these tokens is in a one-hot fashion. So you basically, it's like a vector of zeros everywhere other than in one coordinate, which sort of delineates that, like the which element of the vocabulary the particular token in the sequence is for. So this is some, like, I can kind of lump these in a matrix that's of size little d by capital N. And then the output of the attention layer is the following kind of function. So what I'm going to parameterize this function by is three matrices, which are called the key, query, and value matrices, and correspondingly they're labeled WV, WK, and WQ. And the sort of way that you parameterize the output of the attention layer is you first calculate this softmax expression here. So you basically look at this kind of matrix, which you get by first looking at WKZ transpose times WQZ. This is going to be a capital N by capital N matrix. And then you apply this sort of like softmax function, which makes sure that across, like along columns, this matrix is non-negative and normalized to be of sum 1. So this is like a column stochastic matrix. And then I multiplied out on the outside by WV times Z. So the output here is going to be also a D by N matrix. What means is that for every sort of like token, I produce a D-dimensional embedding after this sort of mechanism is applied. If you've never seen this before, it can sort of be a little bit opaque where this is coming from, and maybe perhaps the easier way to sort of parse this formula is if you kind of write it out by columns. So if you look at the jth column of the output of the attention f of z, what you can view it as is like as a kind of convex combination of the columns of the matrix WVZ. So you're basically combining the columns of WVZ with some with some weights, and these weights are basically how correlated are sort of the kind of the columns of WKZ and WQZ at the appropriate coordinates. So kind of how correlated is the kth column of WKZ and the jth column of WQZ. So you can sort of think of this, the sort of nomenclature here comes from, I guess, like, databases where you think of WK as a query, you think of WK as a key, WQ as a query. So you basically look at how correlated is the key with the query if you look at them as kind of vectors and look at their inner product. And then you sort of like take a weighted combination proportional to kind of the size of this inner product after passing it through the softmax. And then with these weights, you sort of like take a convex combination of the values, which are the columns of the matrix WVZ. Okay, so this is sort of the bare bones, sort of like most basic ingredient of a transformer. Another sort of kind of main ingredient is the loss, and typically with sort of like in sort of NLP tasks, there's really like typically one of two losses that people use. It's either mass language modeling or sort of like autoregressive predictions. For this part of the talk, for the topic model part of the talk, the loss is going to be mass language modeling, and the kind of idea is relatively straightforward. So what you do is you have a sort of some corpus of sentences, maybe Wikipedia or something, and like maybe the sentences Andrew Carnegie famously said, "My heart is in the work." So then the sort of masked in mass language modeling loss comes from the fact that what you're going to do is you're going to pick some subset of the tokens, so some subset of the words in the sentence, and you're going to change them in some ways. Here the changed words are the underlined ones, and the way that you're going to typically that you're going to change them is like you're going to take say like 80% or something of these underlying words, and you're going to swap them out to some new special symbol called mask. So think about it as like, you sort of remove them so the model doesn't know what was in that word. And then with like, the remaining 20%, typically what you do is with some like, 10%, you leave the word to be as it was. So in this case, Carnegie stays Carnegie. And then with the remaining 10%, you change the word to be some other random word. So like, in this case, in got changed to apple. And then what you ask the model is to predict like the words in the sort of like in the underlined positions. So in this case, like the sort of the underlined words, I've swapped them out to question marks to indicate that the model is going to predict them. And then like suppose that we look at one of these positions, the way that now this is going to look is like you're training the model to give some predictions for what should be in this position. So maybe the model thinks that Carnegie with probability 0.05, like Weber with probability 0.09, and so on and so forth. And then like there's some correct label for what the word is supposed to be. In this case, Carnegie. The label is provided by the original token that was there. So in this case, Carnegie was originally in that position. And then like you choose some loss for the prediction of the model at that position. It could be square loss, could be cross entropy loss, whatever you like. And then the sort of total training loss is just the sum over all of the selected positions of these like, losses little l for each of the underlying positions. Okay, so this is mass language modeling. And then the final preliminary is the sort of data model that we're going to be considering. So this is a very kind of like a classical model for understanding topical structure in documents. In some ways, you can think of this as a sort of super simple way to talk about semantics as sort of modeled by co-occurrences of words. What I mean is like, the sort of a topic sort of intuitively will denote pairs of, or like will be captured by pairs of words that tend to co-occur more frequently, and like, two words that are in different topics tend to co-occur less frequently. In another way that sort of maybe like a touch more formal way that you can talk about this is you can think about a document as being a mixture of topics. So these topic modeling distributions are bags of words distribution. So there's no kind of like notion of word order in the documents. And the way that they roughly look is you're trying to sort of represent the relative proportions of each of the possible words in the vocabulary in a document. So for instance, in this case, excuse me, I'm thinking of a document as a list, and for each of the words in the vocabulary, the percentage, like the percentage of times, the percentage of all words in the document that word appears in. So like maybe the first word appears 2%, second word 4%, and so on and so forth. And I'm going to try to represent this word as a mixture of like of certain topics. So maybe I'm going to think about this vector of this probability vector as like 0.7 times some other kind of probability vector of words that correspond to some topics. So for instance, maybe something having to do with physics. I guess that's what this illustration is supposed to be kind of representing. And maybe there's like another topic that appears like point with probability with like a proportion 0.2. That's another kind of vector of words that corresponds to some other topic, maybe something to do with finance, and so on and so forth. So this is a very kind of classical kind of probabilistic model for data that sort of dates back to very kind of early work in graphical models and trying to understand like, the kind of the topical structure and doing some simple unsupervised learning on like, corpora like the New York Times or something. And there's been like over the years a lot of kind of algorithmic work on using techniques like variational inference to learn the parameters of this model. So the parameters would be the relative kind of like probabilities of each of the topics appearing in the documents, and also the relative and also the probabilities of words in each of the topics. And like, more recently, sort of like sometime around like, the 2010s, up to like actually even now, kind of algorithmic work based on using kind of spectral methods, tensor methods, and method of moments to kind of learn the parameters of the model. But in this sort of paper, what we're going to try to do is we're going to try to understand how transformers, when trained on data like this, so basically data generated by a topic model, how do they sort of encode or learn the topic structure, which is sort of the only thing that this particular data model knows about. Like there's no other structure other than the kind of the topics. And actually, even though you might say like, okay, we live in the era of large language models, like, well, why are we talking about like topic models? This is like a bag of words model. There's no even like meaning to the order of the words. Well, because we're trying to understand sort of theoretically what's going to happen when, we're training transformers. So this is kind of very complicated, even on this sort of simple model for data. And in fact, actually, what we do in the paper is an even further simplification. So we actually study a sort of a special case of topic models where the topics that are generating the documents are actually fully disjoint. So you can kind of imagine topics that are kind of very sort of orthogonal to each other. So maybe you have a topic on something having to do with like, quantum physics, like maybe qubits, superposition, entanglement, maybe like, topic 2, the words or something like, biodiversity and ecosystem. And it turns out even in this case, things are not trivial. And like also we need sort of like again, for technical reasons, we need like a variety of sort of like quantities to concentrate to their population sort of version. So we also look at the case where the documents are infinitely long. So we basically imagine we have very, very long documents when we're training the transport.
Andrej, sorry to interrupt.
Yes.
The audio quality suddenly got slightly worse. You sound a bit metallic. It's still understandable, but did anything change in your microphone setup?
I don't think so, but is it better now? 1, 2, 3, 1, 2, 3.
Actually, yes, and also it was understandable. So okay, let's just proceed.
Give me a warning if it happens again, and maybe okay. So I imagine maybe what happened was that the connection broke up, but hopefully it's fine now.
I think we're good. Yeah, thanks.
Maybe it's actually I guess like since I kind of paused for a little bit anyways, like maybe it's a good like a place to pause and see if there's any questions up to this point. I'm not minding. It's a little bit difficult for me to mind the chat, so maybe if you have a question, just like feel free to be not shy and just unmute and ask me. Okay, good. Cool. So this was kind of preliminaries, and so just like to further even further deflate expectations. So as I said, like somehow even this sort of like measly data distribution of like topic models, even with these sort of like extra sort of assumptions, actually turns out that like even this is still hard to analyze. And the problem is that like despite the fact that like there's a bunch of us who've been trying to sort of like work in deep learning theory for like years now, like it's actually kind of analyzing training dynamics is very hard. So actually we don't really know how to analyze even a single attention layer trained with like standard gradient based algorithms like gradient descent or stochastic gradient descent, even on these kind of very simple distributions. So we have to make like further simplifications, but these are, I think, actually useful simplifications because they come from some kind of empirical observations, which I'll give you some intuition where they come from. They definitely make the analysis much, much simpler. So we and sort of like and kind of allow us to understand what's going on at least at some course level. So this is a sort of a simplification and an assumption, but it's like an empirically sort of justified one. So what we sort of observe when we train, like, a variety of transformer-based models is we sort of observe that if we look at the training, there seem to be kind of two stages, which I'm kind of representing on these plots here with like this sort of dotted blue line here. And what happens in these two stages is if I kind of look at so if I look at these three plots, they correspond to the kind of plotting the magnitude of the Frobenius norm of the key, query, and value matrices as training progresses. So x-axis is like, step of training, so further along in training, and then the y-axis is the Frobenius norm of the matrices. So what I observe is that there's sort of like up to this kind of blue breakoff point, the Frobenius norms of the key and query matrices are kind of small, like, so they're basically very, very small. And the kind of the Frobenius norm of the value matrix kind of grows very quickly. So it sort of increases during this like period where the Frobenius norms of WK and WQ are very small, and then after that it switches. So basically, then WK and WQ start growing, and WV basically stays relatively flat. So what this sort of suggests is like and this is kind of a very robust observation. So here's some more plots from like real architectures, meaning like sort of not like toyish like one or two layer models, but like real sort of like transformers trained on like actual data. So in this case, it's on the kind of Wikipedia data set. So these are kind of multi-layer, multi-head transformers. It's sort of the same type of behavior as on the previous slide. Is not as clean. On the previous slide, I was showing you like a very simple one-layer transformer trained on topic modeling data. So sort of the picture is much cleaner, but kind of qualitatively, you still have this kind of two-stage behavior. And in fact, like, the intuition for where this two-stage behavior comes from is sort of relatively simple. So what happens is like here in the bottom right, I'm kind of reminding you what is the expression for the for one layer of attention. So this is sort of the same kind of expression that I showed you a few slides ago. So at initialization, what I'm going to start with is like all of the key, query, and value matrices are small. So I can kind of think of them as being like something like zero, sort of like some cartoonish way. And then early in training, what's going to happen is I'm doing gradient-based training. What's going to happen early on is that WV is going to get larger gradient. So it's going to learn faster than WK and WQ. The intuition for this is when I write down the gradient for WV, sorry, it's for WK or WQ, it's sort of symmetric for both of them. What's going to happen is the other matrix, in the case of WK, you're going to, by chain rule, you're going to have, because of this kind of product here, you're going to get WQ in the expression for the gradient. And WQ is small. So basically, the gradient for WK will be small. And again, symmetrically, the same thing is true for WQ. So the gradient for WQ will be small. But this is not the case for WV, because this, like, WV kind of appears outside. When I kind of write down the gradient for WV, what I'm going to get is like this attention, sort of the matrix with the with the sigmoid being applied to it. And originally WK and WQ are kind of close to zero, so I get sigmoid of roughly zero. Sigmoid of like softmax of zero is just basically going to be all ones. So in fact, like this attention of Z matrix is not going to be close to zero, it's going to be close to uniform. So then basically the gradient with respect to V is kind of large. And so this kind of tells you that originally you expect WV to make progress, and then like, up to some point, and then like, WV to kind of stagnate, and then WK and WQ to make progress. So this is it's not a proof. Like in fact, this is not literally true, but this is like, a simplification that's kind of based on empirical observation that's going to allow us to talk about what are the optima of the training dynamics. Okay, so now, okay, how does this help? So now what we can do is this kind of like analysis where we can write down in sort of almost an explicit form what are the optima of each of these two stages. So in the first stage, we imagine that these stages are fully clean. So in stage one, WK and WQ just doesn't move at all. So it's equal to its initialization value, let's say just equal to zero. So the attention is uniform. And then what you can show is that if you take the sort of simplest one-hot embedding for the tokens, then the optimum for WV, which also will be reached by sort of gradient-based optimization procedures, has like a nicely interpretable block structure, where if you look at sort of entries ij, when I and j belong to the same topic, the magnitude is bigger. And if you look at entries when ij in a different topic, the magnitude is smaller. So if you kind of sort the entries in this kind of way, like in the picture, so that like kind of tokens that are in the same topic are next to each other, you'll get this like kind of nice blockwise structure where the magnitudes are bigger for like entries for like words in the same topic, and they're smaller for the off diagonal. So basically, when words in a different topic. Uh, the proof idea for this is actually very simple because of the simplification that we did. If WK and WQ are frozen, so if the attention is uniform, from the perspective of WV, the objective is actually convex. So I can, in fact, like, if you imagine something like square loss or something, it's just linear regression. And I can basically sort of write out at the population level, when the documents are long, I can kind of write out this loss even fairly explicitly. So I can write down the solution of it fairly explicitly. So I basically have like a very sort of like explicit formula for the optimum WV, and then you can kind of read off that this WV kind of has this block structure that I'm showing in the picture. So this is stage one. Stage two, you imagine that, like, again, we sort of make the clean assumption that these stages are kind of literally the way I described them. So in stage two, you fix WV to be the optimizer in stage one, and then you sort of try to look at what are the optima from the point of view of the attention matrix. So the attention matrix, I'm denoting to be this matrix A, which is like, the sigmoid applied to WKZ transpose WQZ. And what you can show is that the optimal attention matrix is such that entries ij, when tokens ij belong to the same topic, will have a larger magnitude, and entries ij where ij and a different topic will have a smaller magnitude. And in this case, if you're kind of perceptive, you'll notice that I've said, like, if gradient descent reaches it. So the reason why this is not as simple as in the previous case is that the loss in this case is convex from the point of view of the matrix A. So if you denote this entire sort of attention matrix A, it's convex as a function of A, but it's not convex as a function of WK and WQ. So if you actually try to analyze the training dynamics when you're kind of like, training the parameters, of the model, which will be WK and WQ, this would be some kind of like, complicated nonlinear matrix factorization problem, which actually we don't know how to analyze. Like, so these are kind of fairly complicated problems that, like, people spent a lot of time thinking about, even in the case where there's a kind of no nonlinearity outside like the sigmoid. But anyways, if you sort of focus on the matrix A, then again, sort of the proof sketch for why you can kind of prove this kind of, again, blockwise structure where the tokens, where like the attention is bigger when the tokens are in the same topic is the reason is still the same. From the perspective of A, the loss is convex as a function of A. And again, like if you're in the scenario kind of at the population level when the documents are long, the loss kind of simplifies. And so it simplifies enough that you can write down something that's like a semi-closed form expression, and then you win. Like that's basically the more or less the gist of it. And if you sort of are a little bit kind of skeptical, we also did sort of checks for whether the pairwise attention tends to be bigger for actual kind of real trained models. And I appreciate that this is like a very big table, so let me just shade some parts of it here just to kind of convey what the message is. So what we have here is the kind of what we do is we basically fit a topic model on like data from Wikipedia. Once you fit a topic model, then you have topics, and then you can kind of speak about the average sort of like attention value, or average like cosine similarity, or average like basically all of the sort of like expressions that I was showing you in the previous two kind of theoretical results for words in the same topic and for words in a different topic. And what happens is like the results kind of qualitatively at least track the results previously. So what you'll see is that like if you look at the attention weights, the ratio of the attention weights in the same topic versus a different topic will be bigger than one. If you look at actually even the embeddings, like they will also be kind of, that's in the shaded thing, like the embeddings, if they're learned, they will also kind of be bigger for words in the same topic compared to words in a different topic. So again, the ratio will be bigger than one. So altogether, like, of course, on real data, things are messier because real data isn't really topic models, but this overall kind of like a sort of interpretable structure of having on kind of like on average bigger pairwise sort of like attention, or like bigger sort of like inner products for embeddings and so on and so forth. They're tracking kind of the theory fairly. Okay. So Maybe let me kind of pause here for a bit and see if there's any questions, because then I'll switch gears and start talking about context-free grammars for the next bit.
I I have a question. Can you hear me?
Yes.
Okay. So the both of the methods, like looking to the weights from key and look to the weights from the transformer metrics, they have the same confiability.
They have the same, sorry, the last word I didn't catch.
Confiability, like they you show exactly the same behavior for the same topics.
Oh, I mean, it's not like quantitatively the same, but qualitatively, like you get this kind of blockwise structure that you get from the theory.
Okay. Okay.
Yeah.
Thank you.
Yeah.
Hi.
All right. Oh, sorry. Good. Yeah.
Oh, sorry.
Go for it, please. Yes.
Okay, a quick question then.
Yes.
So a couple slides ago, there were these graphs where you you were checking the increase of the Frobenius norms of these three matrices.
Yep. Yep.
But for the Frobenius norm of the WV matrix on the real world data, on the real world, so if you go one
on the real world data, yeah. Yep.
there seems to be like a double increase, like a two-step thing.
Yeah.
Do you have any hypotheses, ideas about that?
No, yeah, this is curious and seems to happen with like certain sort of certain initializations and like certain. So I'm actually not sure like if this is there's like sort of slight differences in the plots you get if you use atom versus if you do small step size SGD. And Yuchen is I think also on the call. I think we tried to sort of poke a little bit further, and I don't think we had any like good explanation for why this happens. But correct me if I'm wrong, Yuchen. Yeah, he's not correcting me, so I guess he's not correcting me, so I guess I didn't say anything wrong. Yeah.
Okay, thank you.
I will say one thing, like so basically the theory assumes that for the second stage, WV doesn't change at all. It definitely does change. So like what you can actually track is like you can see that the norm doesn't change, but it kind of rotates. Like so there's sort of like changes from one step to another. So this is definitely a simplification. It's not so easy to actually like qualitatively kind of pick out something from the experiments that tells you like in what way is it rotating, but like that's definitely somehow a useful simplification for the theory that's not actually.
Okay, very interesting. Thank you.
Yeah.
Okay. Can I ask one last question?
Yes, of course.
What happens if you don't start from zero? So I understand the story when you initialize near zero, but in practice you would initialize to something random with some variance for WV, WK. Is it still true? Does it still happen, this phenomenon?
Very good question. So if you initialize with like sufficiently small random initialization, same story holds. If you start making the initialization be like bigger in magnitude, this sort of like sharp kind of switch over gets progressively less sharp, and at some point it's like not particularly sharp. It's sort of the case that with the standard initializations, you see it to some degree. You definitely don't see it as cleanly as you see it on the sort of like I guess like a cleaned up kind of like toy data with like smaller initialization. So yeah, it's messier when you don't have like small initialization.
All right, and you still converge to this nice, let's say, representation of topic modeling in the attention matrix? Or
yes, qualitatively, you still see like pairwise attention being bigger by and large, like for a lot of the heads, for things in the same topic. Yeah.
I see. Thanks.
Yeah. Excellent questions. All right. Good. Okay, so let me tell you now about the second part. So this is going to be sort of like a part about another kind of like simple linguistic sandbox. It's going to be about context-free grammars. So this is a joint work with my students Yuchen and Bingbin and Kaiue, who was at that point like a undergrad from Tsinghua visiting me at CMU, and now is like a very successful grad student at Stanford. So let me tell you sort of what the sort of story is here. So what are kind of context-free grammars? So kind of topic models largely are sort of some very simple model of semantics. So they kind of tell you what words tend to co-occur based on whether kind of topically they're sort of like talking about the same thing or not. If you want to kind of capture syntax, possibly the sort of simplest model for this is context-free grammars. In fact, like, there's a whole bunch of, so I'm showing actually this like very cool, I guess, like graphics. So people in linguistics have even done work where they try to analyze specific like spoken language, like written or spoken human languages, and they try to kind of understand where they lie in what's called this like Chomsky hierarchy. So they try to sort of understand how complicated from the point of view of like formal language theory, like real sort of spoken languages are. Context-free grammars are kind of arguably sort of one of the simplest sort of like formal languages to talk about sort of syntax. And I'm actually going to talk about what's arguably the simplest context-free grammar, which is the sort of grammar of balanced parentheses of different types, or what's called a dyke. Okay, so what is a dyke grammar? So it's this sort of formal language where the strings that belong to the language are strings which kind of form validly nested or like balanced parentheses. So for instance, if you have a string that looks like this, you can see, there's possibly different, kinds of brackets. So in this case, there's square brackets and round brackets, and you can see that all of the kind of brackets are nested sort of like, the correct way. Same thing here, like, the curly brackets are nested the correct way. Then like outside the kind of square brackets are kind of, again, nested the correct way. And then outside the round brackets, again, nested the correct way. And then here's like an example of an invalid string. So you have like an opened, square bracket, and then like it's being closed by a round bracket. So that's null. And you can imagine sort of training a transformer model. In this case, it's going to be an autoregressive model where you kind of try to get the model to predict, let's say, the type and the openness of the next bracket. So it's basically trying to predict what the next token can be. Tokens in this case just sort of correspond to whether, what kind of like bracket you have. And you can sort of imagine this sort of the simplest case where maybe you're looking like, so you're just trying to kind of predict what is the type and the openness of it. And so why is this like a natural formal language? And sort of why did people, even on the empirical side of things, start to study this as a sort of a sandbox for understanding what transformers learn? It's almost kind of definitionally, there's a natural algorithm to sort of decide whether a string in this language, whether a string belongs in this language or not. And it's basically just simulating a stack. So what do I mean? Like, if you just look at this sort of little animation, the sort of natural way to detect or decide whether the string is in the language or not is you march left to right. Every time you see an opening bracket, you add it to the stack. So you've seen like an opening, square bracket added to the stack, opening curly bracket added to the stack, opening round bracket added to the stack. And then when you see a closing bracket, you try to pop off the stack if the bracket is matching. So in this case, I see a closing round bracket. The top of the stack is an opening round bracket. So that's correct. I pop it off the stack. And then again, I see a closing curly bracket. At the top of the stack, I have an open curly bracket. So again, I can pop it off the stack. And if at any point you need to pop the wrong thing off the stack, that just means that the string is not in the line. So this is basically the sort of simplest algorithm for how you might recognize whether a string is in the language or not. And you might kind of ask the question, how do transformers process this language? So the story sort of starts here with the kind of work in the kind of early 2020s, like maybe the first paper to kind of like study this is this paper by Brahimi et al. And then there was kind of theoretical kind of follow-ups by Yao et al., where sort of like there was an either implicit or explicit conjecture that transformers learn how to solve this next token prediction task for dyke languages by sort of attention that has some very interpretable stack-like a pattern. And what I mean by that is kind of what's on the picture here. So what sort of like the sort of informal conjecture was is that somehow what you expect is that the attention will be such that whenever you're trying to predict what is the next token in a particular position, you do so by attention that sort of focuses on the last unclosed bracket and sort of like, doing something based on what you see there. And if that were the case, what you would see is these kind of like, staircase types of patterns, because what happens is when you have an opening bracket, so like, here you have an opening round bracket, and then you just like, the last like, unclosed bracket is just the current one. So whenever you see opening brackets, you sort of see things on the diagonal. And then when you see a closed bracket, then you sort of like, pop something off the stack and like the way that it manifests on the kind of, with this conjecture is like you sort of move back the sort of the attention like to the sort of previous unclosed brackets. So sort of in this case, for instance, the kind of the opening bracket would have been like, this like round bracket. And then once that gets popped, like the last kind of unclosed bracket is the kind of the very sort of first opening round bracket. So like, your attention is all. And okay, so our result is that basically this is certainly a way to solve the problem. And in fact, this kind of Yao et al. Paper had a very nice kind of representational theoretic result that said that there exists like a network that actually does this by kind of attention that looks like this. But what we show is that sort of in the wild, like when you train transformers on data that comes from these like languages, even if you sort of incentivize the transformers a lot by kind of giving them the right sort of like, inductive bias by helping them like, in certain parts of the layers, I'll tell you what I mean by that, they still kind of learn very diverse attention patterns. And sort of in theory, we can just prove that there's like a variety, there's a variety of sort of like attention patterns, many of which look nothing like the stack-like pattern that actually solve this task. And actually, if you train transformers, like you will see a whole bunch of different diverse attentions, which is sort of what I'm showing here in these points. And this is not like I'm giving you cherry-picked models that somehow didn't actually do well on the task. Like you get these diverse patterns even among models which have a very high performance, like reach basically almost 100% accuracy. Okay, so here's roughly what the results say. So result one says that if you look at even two-layer transformers, you can construct two-layer transformers that give you sort of like optimal loss, meaning like they're optimal in terms of the kind of task of predicting the next token with almost any attention pattern. So for instance, you can make the attention in both of the layers to to be uniform. And this is even kind of true if you fix the first layer to have some very natural form that's inspired by these like constructions, theoretical constructions, where sort of the output of the first layer for every token is sort of depends kind of only on the type and depth of the token in that position. So I'll tell you what this means. And then the other result is that maybe perhaps even more kind of severe, which is that if you take any two transformers T1 and T2, you can kind of always transform, you can construct kind of equivalent transformers T1 prime and T2 prime that sort of like, implement the same circuit. So like T1 prime implements T1 and T2 prime implements T2. And for any kind of fixed component of T1 prime and T2 prime, they agree on this component. So if you kind of myopically only kind of zoom in on one component, T1 and T1 prime and T2 prime are going to look the same, despite the fact that they're sort of implementing some arbitrary, like, different circuits, T1 and T2. And then empirically, what we show is like, even with this kind of natural restriction on kind of the form of the output for the first layer, even with like two-layer transformers, there's basically like, a whole like, host of like different attention patterns that you converge to, just kind of like when training with standard kind of gradient-based, I guess, like procedures. So let me try to flesh out the first result a little bit. So first, let me tell you what this natural assumption means if I'm building a two-layer transformer, like on the kind of outputs of the first layer. So we call this a minimal first layer. So this assumption says that if I look at the outputs at a particular position, the outputs at a particular position only depend on two things: the type of the bracket at that position. So in the kind of examples they were saying, is it like a round bracket? Is it like a square bracket? And so on and so forth. And the depth. So what is the depth? So the depth is sort of the depth of the nesting of the brackets. So for instance, if I imagine that I have I'm just going to roll a sequence, and I'm going to tell you what what these types and depths look like. So for instance, if I see an opening square bracket, the type is square, and the opening square and the depth is 1. Then if I see a closing bracket, the type is closing square, the depth is 0. If I see an open curly bracket, the type is open curly bracket, depth is 1 because I added an opening bracket. Then if I see another opening bracket, say like, this, like angular bracket, then now like the type is angular bracket and the depth is 2 because I've added like another opening bracket. So the sort of minimal first layer is like anything, it can have any functionality, so long as it has the property that it only depends on the bracket type and the depth. And kind of why do we even care about this? Sorry, maybe this is not super visible, but this is a natural sort of assumption because these kind of theoretical constructions that we're trying to engineer sort of a construction so that the sort of second layer has this kind of staircase pattern that was conjectured, exactly have outputs at the first layer that have this sort of kind of structure. So the outputs only depend on the type and the depth of the bracket. And then sort of the theorem that we can show is that the kind of any two-layer transformer where the first layer satisfies this kind of minimal condition, in order to be optimal on Dike, so in order to have like optimal error in terms of predicting like, the next token, the kind of the if and only if, so the necessary and sufficient condition is that it satisfies what we call a balance condition. So this balance condition says the following. So it's sort of like some kind of quadratic form where on the left, what we have is for every sort of like type of bracket, let's say square, I look at sort of the difference between the embeddings that are being produced at the first level for like the opening kind of bracket of that type at depth d minus the embedding for the closing bracket of that type at depth d minus 1. So that's sort of like one vector that I hit this quadratic form WK transpose WQ with. And then on the right, I have the difference of like, the closing brackets sort of like for any two different types, say in this case, like, closing curly bracket and closing angular bracket at two depths d1 and d2. And this form, this sort of quadratic form needs to be equal to 0 for, so the quantifiers here are on the kind of left, you iterate for every type of like bracket. So, and then like, the opening and closing need to match. So in this case, it's like a square bracket. And then on the right, it's for every pair of like, two types. So in this case, like it's like, for type like, curly bracket and type like, angular bracket. So where does this come from? It's a little bit like kind of involved to tell you where exactly the proof comes from, and I'm not going to do it. But basically, what this sort of roughly what you should think of this is if you've seen like, some of these things in your, I don't know, like undergraduate, either algorithms or automata class. I don't know if folks these days still take automata classes. I had to take something that had automata, but basically the idea for this sort of like type of is for kind of for the behind this theorem is that in some ways you want to say that when you have matching brackets, so you basically, if you've sort of like matched some opening bracket to some closing bracket, or you can also imagine kind of the popping procedure for the stack that I showed you, they should kind of, once you've matched two brackets of the same type, they should sort of not affect the final prediction. So somehow like their contribution to the output of the model should in some ways cancel out. That's kind of what this condition, if you translate it appropriately, what it's basically saying. This is sort of why you have this kind of difference on the left-hand side, and then there's some sort of like calculations that you have to do, but that's sort of roughly the idea. And then also sort of somewhere underneath the hood, there's like some kind of pumping lemma style argument where you sort of try to see sort of for the only if side of the direction, you sort of try to see what happens if you keep inserting pairs of matched brackets and then try to see how the prediction of the model changes. And turns out that if you kind of put these two things together, you get that this is a necessary and sufficient condition for sort of a two-layer transformer with this minimal kind of first layer condition to be optimal. Okay, why am I telling you this? What does this have to do with like interpretable patterns? I'm telling you this because it turns out that this balance condition is in fact a very weak condition. In fact, you can construct a two-layer transformer where both of the layers basically have uniform attention. So clearly here, actually, this condition is satisfiable with uniform attention. Just set WK and WQ to 0. If you have WK and WQ being equal to 0, this is trivially satisfied. And like, that just corresponds to uniform attention. But turns out that like, for Dike, you can kind of construct a minimal first layer with uniform attention as well. Okay, if you have causal masking in a fully connected layer, but nevertheless, you can construct, one layer in which you can encode like, the depth and type with uniform attention as well, so that you can kind of implement a minimal first layer with uniform attention. And then, like, by this theorem, you can also set the second layer to be minimal. And so you have like an architecture where everything is like uniform attention, and yet, like, it solves the task. So this is kind of worrying, because it's basically telling you that even uniform attention, in principle, there are kind of constructions with uniform attention that solve the task that we're interested in. But you might say, perhaps this is just a theory, perhaps we're just sort of somehow pessimistic. Maybe let's just go off and try to train some models. And so this is also true when you actually just like train empirically models. And it's also true even if you freeze, let's say, the first layer to be minimal, and we kind of pick off several natural constructions for minimal first layer, and we just train the second layer. So we're kind of, this is why is this sort of like good from the point of view of this observation about variety of attention patterns? Like, when I freeze the first layer to be minimal, I'm giving it even more kind of hints that this is the architecture that I'm kind of helping you represent. Even if I tell it to do that, it still basically finds like a whole bunch of different constructions for the attention in the second layer. And again, this is kind of not cherry picked, so you even get this sort of a variety in terms of the attention patterns, even if you sort of zoom in on the nearly perfect sort of models, which have like nearly perfect accuracy. So this is one of the results. Here's the other result. So the other result that in some ways, if you zoom in on individual components or individual layers, you can kind of garble them arbitrarily. So what I mean by this is, like, if I hand you any transformer, turns out that you can produce a polynomially larger transformer, TL, which has just random weights. And then this layer, this like original transformer of interest T, can be somehow approximated by pruning, meaning zeroing out some of the kind of weights of this bigger transformer model TL, which has fully just randomly chosen weights with high probability, of course. How does this work? It turns out that the way that this works is you adapt the proof. I mean, even the statement should kind of remind you of this. Like, there's a kind of phenomenon that people were very interested in the last few years called the lottery ticket hypothesis, where basically there's sort of like what are called provable versions of this, where you can show that these works kind of worked with fully connected networks, or rather feed-forward networks rather than transformers. And they showed that for any feed-forward network, you can realize it as a pruned version of a polynomially larger feed-forward network with random weights. The kind of paper that serves as inspiration for our proof is this very nice paper by Pensia et al. So we kind of adapt this proof for transformers. But pictorially, this is the picture. Anything you can kind of realize, any transformer you can realize is a pruned version of a larger random transformer. And it turns out that as a corollary of this, you can show that if I hand you any two transformers T1 and T2, I can realize them both as pruned version of some larger transformer TL with random weights, such that sort of for any fixed component I pick, and component here can be very flexible. It can be one attention head, it can be one fully connected layer. Like, the proof is kind of fairly flexible. I can make sure that the prunings agree on this one fixed component. So if I choose some particular head of this bigger transformer, I can make sure in the pruning that when I'm trying to produce T1 and T2 by the pruning, this particular attention head is the same for both the pruning corresponding to T1 and T2. And this is kind of bad. It's bad because it's telling you that if you're somehow hoping to do any kind of interpretability method where the thing you do is you focus on individual components, like you decide to look at what does the attention look like at layer 3 head 5 or something, you're kind of out of luck. It's basically saying that in some sort of worst case sense, you can realize kind of any fixed component. You can kind of make any fixed component be the same for even any two sort of circuits T1 and T2 that have arbitrarily different functionality. And yet another way to say this is if you sort of want to understand what circuit the model is implementing, you better do something more global. You better not just sort of look at individual components. Okay, so maybe let me, because I realize I'm a little bit over time, so let me maybe just conclude, and then I'll open it up for questions. I guess for the first part, you guys asked some questions, but maybe let me just have one slide of conclusion, and then we can go back and talk about any questions for the second part. So let me sort of maybe just like, give you some tidbits for sort of takeaways. So one is, I want to advocate this sort of like I guess like research philosophy of using simple sandboxes, whichever might be the appropriate sandboxes, as a kind of useful tool for diagnosing failure modes of whatever it might be. Like in this case, we're talking about interpretability methods, but I think this is kind of as a research philosophy, it's a very useful thing. Like somehow sandboxes can be perhaps unsatisfying if you're trying to prove positive results, but if you're trying to prove negative results and you're trying to find sort of like failure modes, it's kind of useful. It's kind of useful to demonstrate them even in kind of very simple ablated settings where you can kind of understand very carefully what's going on. On this kind of last point of myopic methods, there's a variety of sort of like methods that have kind of cropped up anywhere from this kind of circuit level analysis in this anthropic work by Elhag et al. And Olsen et al., which certainly kind of evade these kind of myopic method limitations that I showed in the kind of previous couple of slides. But again, I want to caution that like none of these methods at present has any kind of like kind of theoretical guarantees. And in fact, I suspect sort of at full generality, even if you're allowed to do something non-myopic, but you're kind of computationally bounded, there's probably some sort of like obstructions that you can transfer due to a kind of obfuscation results from cryptography. So we have these kind of like very kind of beautiful results in theoretical computer science that sort of like show that in some kind of like, cryptographic sense, you can take a program and kind of obfuscate it in some ways, such that for any kind of polynomial time adversary, like, they can't sort of like tell what's going on from the obfuscation. I suspect this is probably also the case in sort of some full generality, even if you're allowed kind of holistic methods, but sort of computationally bounded methods for inspecting the train model. I guess what this says, like, I don't want to kind of make this seem like it's kind of very negative or sort of like very pessimistic. I think just all that this means is that if we're trying to kind of understand what kinds of like, guarantees or what kinds of like wins we can kind of hope to get out of these methods, even if we're just using them as diagnostics for understanding like, roughly what a trained model is implementing or not, we probably need to sort of make some additional assumptions, probably guided by some kind of empirical observations. For instance, like one thing that's kind of recently become popular is this kind of linear representation hypothesis that sort of roughly says that in many trained models, it seems like, a lot of useful concepts seem to be implemented as linear functions when looking at some like, particular layers of the trained model. So probably we need to start thinking about like, sort of benign sort of assumptions that kind of obviate these lower bounds that say that kind of in some level of generality, the method, whatever interpretability method A or B or something has some flaws. And so maybe with that in mind, like, I want to wrap it up here and maybe open it up for questions. And I'm sorry, I went a little bit over time, but not too much. So thanks for the attention, and yeah, thanks for the invitation again.